So the Nobel Prize of Chemistry in 2023 was awarded to Moungi Bawendi, Brus and Alexey Ekimov for the synthesis and discovery of colloidal quantum dots. A quantum dot is a tiny piece of semiconductor, and it's so small that the electrons start to fill the walls of the particle itself. And this is basically the real-world example of a particle in a box, the quantum mechanical particle in a box. So as you make the particle smaller and smaller, you are squeezing the wave function of the electrons that are in the particle. And as you're squeezing the wave functions, the energy levels, they start to separate more and more. So the properties of the semiconductor, of this nanoparticle, suddenly start to depend heavily on the size of the particle. So if we can control the size of the particle, you can control the property. So one of the most striking things of these changes in the properties is that the color changes. Because when you change the level spacing of these particles, when you make them smaller and smaller, the energy of the photon that is needed to excite an electron also gets to be bigger and bigger. So you need bluer and bluer wavelengths to actually create the excitation. So what they studied in the early 80s, and this was Alexey Ekimov, to look at glass windows, colored glass windows that we know from the churches. They contain tiny particles, metallic particles or semiconducting particles. And in this case, in the semiconducting particles, what he was trying was new techniques to make these particles smaller and smaller. When they were so tiny, he started to see color changes. And using X-ray diffraction, he could correlate the change in size with the change in color. And this was really a first observation of this kind of large-scale fabrication of tiny semiconductor nanoparticles. Now, around the same time, Brus was doing a very different kind of technique, synthesizing with chemical techniques these kind of particles from the bottom up. Yeah? And this was in solution. So now he was observing similar things, that when you were really controlling the size of these particles, that the colors would change. Now we have to take a jump, right? Because to really control the size of these particles, we have to think that these particles are a few nanometers in size. So already just adding a few atoms to the particle makes a huge difference. So you need to have atomic scale control over these particles to really control which color of particle you're gonna synthesize. So in the early 90s, Moungi Bawendi, which was a former postdoc of Brus, he just started this group at MIT as a young assistant professor. And with his generation of first PhD students, Christopher Murray and David Norris, they started to really push, can we control these particles on such a scale that each particle in the giant ensemble, billions of particles that you're synthesizing at the same time, can they all have exactly the same properties? Can they all have exactly the same size? And they developed what is now referred to as hot injection synthesis. And this is kind of a counterintuitive idea, because all these reactants that you have, they are very reactive. You would think that you want to have a very mild synthesis where things grow slowly. They went to the exact opposite. Yeah? So hot injection means that you are putting your solvent to a boiling temperature, you're injecting your precursors, and everything starts to ignite at the same time. So you have all these little tiny crystals that all start forming at the same time, and they start growing at the same time, at the same rate. All particles at the end up with the same size, meaning that you are really controlling the optoelectronic properties of these particles. So old-fashioned semiconductors, they are used all over to collect or generate light. We can think of the sensors in our camera or the light-emitting diodes that we are using. But one of the issues is that with conventional semiconductors, the properties are fixed. So the colors that we have are the few semiconductors that are available to us. After the whole hot injection synthesis, now suddenly we can create semiconductors in solution as an ink. So this means that now you can make LEDs of any color that you want, or you can make photodetectors, camera sensors that are sensitive to specific parts of the spectrum of light. And this really is where we are right now. So if we look on the market, we already have the QLED televisions where the traditional organic semiconductors have been substituted for quantum dot semiconductors, simply because they are with colors that are much better defined than the organics. What people are really interested right now is really using the quantum properties of these quantum dots, right? So we have this very nice particle in a box, and can we now start using those for information processing applications, for example? And so for that, there's still some challenges ahead. Physicists like to have the perfect particle in a box. Chemists will tell you that that doesn't exist. So there's still, some development in the synthesis to make them even better and cleaner, such that we can start using them for those kind of applications.